So I'd like to start by thanking James and the organizers for putting together this very interesting meeting. And secondly, I'd like to thank the previous speakers in this session for providing all the background for my talk. So I'm just going to jump right into it. Okay, so today we heard a lot about charging. I'm going to focus more on storage and a bit of discharge in a quantum battery. And our motivating goal is to basically store energy in the form of excitons in an open quantum battery, so a battery that's coupled to an environment or environments without loss for as long as possible. And being a chemist and learning a lot about spectroscopy, we've heard about dark states a lot. So the idea of a dark state, using dark states, which are just quantum states that do not emit photons, at least in an ideal situation, thinking about this possibility of using dark states for exciton storage. So the main question that we're trying to answer here is, can one design an open quantum network that supports dark states? Okay. So on the right here, basically, the hope is to extend the exciton lifetime of the quantum battery, so to sort of reduce the losses via radiative and non-radiative pathways. Okay, so here's our open quantum network model. So it's shown here on the right. We considered a 6-site model, where at each site you could imagine a multi-level quantum system, 2 levels or 3 levels, whatever you like. So that could be 2 levels of an atom or a molecule or a quantum dot or whatever. And this is our general Hamiltonian. So we have our network Hamiltonian, or our battery Hamiltonian, plus the network bath coupling, plus the bath Hamiltonian. Okay, so our network Hamiltonian is sort of a typical Frankel type exciton Hamiltonian, where the first set of terms involve the site energies of the various sites in the network, and the JNMs are the transfer integrals or the electronic couplings between the various sites, and we consider only in this study nearest neighbor couplings between the sites. And the states that appear here in the Hamiltonian are single excitation states. So for example, state 1 means that I have an excitation on site 1, and all the remaining sites are in their ground states. Okay, so that's what the Hamiltonian matrix looks like with the nearest neighbor couplings. And the bath and network bath coupling terms are, so basically we consider bosonic bath of harmonic oscillators, and the coupling between the bath and the network is of a bilinear form, as you can see here. And the NNs here correspond to sites 1 and 4. As you can see, they couple to the thermal baths at temperature T. Okay, so the question is, can this network that we just talked about support the existence of dark states? So it turns out that the answer is yes, in a very ideal situation, which I'm going to elaborate on. So if we take the energy, There we go. So if we take the energy of site 1 here, the one that's coupled to the left bath, to be greater than the site energy of site 2, which is equal to the energy of site 3, which is equal to the energy of site 4, which is equal to the energy of site 6, and all of those greater than the energy of site 4, which I'm going to term the exit site, since it's the site with the lowest energy. And on top of that, if I take the coupling between 1, 2 to be equal to 1, 6, the coupling between 2, 3 to be equal to 6, 5, and the coupling between 4, 5 to be equal to 4, 3. So under those conditions, one can write down a symmetry operator, which looks like this. So 1, 1 plus 4, 4 plus 2, 6 plus 3, 5 plus the Hermitian conjugate. In addition, if this symmetry operator satisfies these commutation relations, so namely that the symmetry operator commutes with the network Hamiltonian, and in addition, the symmetry operator commutes with the coupling Hamiltonian. So if you recall, the coupling Hamiltonian had this NN projector in it. So one can show, I'm not going to go through all the details due to lack of time, that this open quantum network supports dark states, one of which is shown here. So 1/2 5 plus 6 minus 2 minus 3. So that's the state that's sort of a linear combination of the what I call the bulk states, sites 2, 3, 5, and 6. And you can see there's no contribution from sites 1 and 4. Okay, so if these two conditions are satisfied, it turns out that the composite dynamics generated by the total Hamiltonian, so the dynamics of both the system and the bath, generated by the total Hamiltonian, leaves these dark states invariant. So the idea was, can we use these dark states for energy storage? Okay, so we need to store energy, and then eventually we need to discharge it. So how do we do that? So we just break the symmetry. So what we did is we attach what we call a symmetry breaking perturbation to sites 2 and 3. There's nothing unique about that. You can attach a symmetry breaking perturbation wherever you like. And this is the total Hamiltonian. So when chi is equal to 1, that corresponds to the Hamiltonian for the discharge phase. And when chi is equal to 0, that corresponds to the Hamiltonian for the storage phase. Now I call it the probe and the network probe Hamiltonian, again, is another thermal reservoir at some temperature T. In this study, we kept all the temperatures constant for all the baths. And this is the S operator corresponding to attaching to sites 2 and 3. Okay, so when we break the symmetry, the reduced density matrix for our quantum battery leaves the dark state subspace. As a result, as I'm going to show you, the exciton transfers to the surface sites. Okay, so how did we simulate the excitonic dynamics of this system? So we used a mixed quantum classical method that we actually developed in our group some years ago, known as the DECIDE method, which stands for what you see here, a mouthful. Basically, in this mixed quantum classical method, we treat the network quantum mechanically, and the bath, the harmonic oscillator baths for the left and right baths, and also for the probe, are treated in a classical-like fashion. And this method has been shown to be accurate on a variety of models that we studied previously for excitation energy transfer. So we have confidence in the method. And because it's a mixed quantum classical method, we have a couple of advantages, namely that it's computationally efficient for systems with many bath degrees of freedom. So if I have like hundreds or thousands of, let's say, oscillators in the baths, not really a major problem. And secondly, we can actually treat more realistic systems using a mixed quantum classical method. Okay, so a few more details. So as I said, the network, which we're treating quantum mechanically, these are the coordinates, these sort of operators involving the N and M states. The bath coordinates, because we're treating them in a classical-like method approach, we have position and momenta for the bath coordinates. And the network bath coupling is characterized by a Debye-Druid spectral density, although we could have used any spectral density, where the bath reorganization energy here, lambda, characterizes the strength of the coupling between the network and the bath. So these are the equations of motion that we solved. We solved the system of equations of motion. I won't get into the details. And ultimately, we computed expectation values. So basically, we just generated a large ensemble of trajectories on the order of at least 10,000 to maybe a couple 100,000 trajectories. And we could do that quite easily. And we computed these expectation values. So all the results that I report are expectation values of populations and energies and so on. And weighted by this initial density matrix here, where the initial state is, so I'm initializing the open quantum network in the dark state. I'm not talking about how to charge the battery, that's a separate story. And the baths are in a thermal equilibrium state at temperature T. And these are the simulation parameters that we happen to use. Okay, so I'm going to start by presenting the results without any disorder, and then I'm going to show the effects of different types of disorder on the exciton dynamics. So in the storage phase, when chi is equal to 0, you see that the populations of sites 2, 3, 5, and 6 remain constant. This would go on forever at 25% apiece. Okay, and the sites 1 and 4 remains 0 forever. Okay, as soon as you introduce the symmetry breaking perturbation, things start to change. So we see that the population of the exit site, site 4, increases to about 25%. The population of site 1 increases to about 11-12%, while the populations of the other sites begin to decrease. Okay, so that's what happens. So we're discharging to the exit site, site 4. Okay, and on the right here I show the energy changes. So during the storage phase first, so I've broken up the energy changes into the left bath energy, right bath energy, system energy, and the total energy. You see that there's no change across the board, so zeros. However, when you break the symmetry and during the discharge phase, we see, just to give you a couple of examples here, an increase in the right bath energy. That's the bath that's connected to the exit site, and a decrease in the network energy over this time scale of picosecond. Okay, just quickly, if you increase the energetic bias, so that is the difference in energy between sites 1 and 4, from 250 to 400, you see that you can direct more population towards the exit site, okay, and suppress the site 1 population. Okay, so we can explore the whole parameter space of the model, which we did, but I'm not going to get into that today. Okay, now, what if in a real system, there's going to be disorder? That was an idealized system. Everything was perfectly symmetric. In a real system, there will be disorder. I'm going to talk about diagonal disorder, so introducing disorder into these site energies here, but we could also talk about off-diagonal disorder, but I just don't have time for that today. And the results are not so, are not qualitatively different. So I'm going to show you the results for 2 types of disorder, namely starting with static disorder. So static disorder, as the name implies, is time independent. So basically at the start of each trajectory, we introduce these static disorders. We add, let's say, some small change, or add or subtract some small change to the site energies. And basically in doing so, we're capturing the effect of different local environments around each site. And we're sampling the disorders from a Gaussian distribution with some width sigma there. Okay, and the second type of disorder that we consider is a dynamic disorder. This is a time-dependent disorder. So at each time step of the trajectory, we add disorder. We consider 3 types: sinusoidal function, where we basically randomly sample this phase shift here from this interval. White noise, whose correlation function is basically a delta function here, and colored noise, so some correlated noise where the correlation time is tau c here. Okay, so I'm going to present results for these various cases. So dynamic disorder could, for example, capture the effect of temperature, causing the atoms to fluctuate, whereas static disorder could correspond to some defects in the lattice, for example. Okay, so starting with static diagonal disorder during the storage phase using these parameters, I'll just draw your attention to the site 4 population, so the exit site population. Basically, we see that under weak disorder, so 2 wave numbers here, which is about 1% of the site energies of the bulk sites, does not significantly affect or degrade the storage efficiency. So we have no leakage here. However, as you increase, as you would expect, the disorder, you get significant population loss. Okay. Now on to the discharge phase. Again, for static diagonal disorder. Again, focusing on site 4. We see that weak disorder does not affect the discharge dynamics. So all these curves look roughly the same. Even as you increase the strength of the disorder, not much difference. Okay, moving on to dynamic diagonal disorder during the storage phase, considering the sinusoidal phase shifts here. At least for these parameters, so for an amplitude of 5 wave numbers, which is relatively small, we see very small population leakage, which I define as the leakage to the surface sites. So fairly robust to phase shifts. Now, comparing color to static to white noise, basically what you see if you look, let's focus on the top panels here. that the population leakage in the case of static disorder is larger than the case of color, which is larger than in the case of white noise. If you look at the numbers here, you'll see that. And basically, this is a reflection of the ability of these different types of disorder to restore the system to the symmetric or near symmetric conditions. Okay? And when we remove the baths, basically we see that there's less population leakage without the baths. Okay, am I out of time? Okay, let me just skip on to this decoherence dynamics. So I just calculated also the purity. As you can see during the storage phase, since the dark state exists in a decoherence-free subspace, the decoherence, there's no decoherence, the purity is 1, and then as you increase the symmetry breaking, you see that the decoherence increases. Okay, that's the summary, and I'd just like to end by thanking those who are involved in the work. My former postdoc Junji that started this work. We also collaborated with Gabriel Hanna from the University of Toronto, Zahre here, my current PhD student who did all the symmetry breaking work, and I would like to thank you for your attention.
I think we have time for one very quick question. So, up front here, please.
Thank you very much for the amazing talk. It actually straightforwardly faces this problem of storage and leakage under like quasi-realistic conditions of disorder and noise, and it's a solvable model as well. My question is about methodology. You solve the quantum equations and the Bath classical equations simultaneously. This is the first time I saw this. In all the other talks, there's this Lindblad master equation where the Bath degrees of freedom are integrated out, yes, and they just show up as non-Hermitian terms in the equation. Could you please underline like what is the necessity for simulating the classical dynamics of the Bath?
Yeah, so I come from a chemistry background, and in theoretical computational chemistry, quantum classical dynamic methods are fairly common. And my background is in mixed quantum classical dynamics. So we developed this pretty efficient approach, this decide approach. And I decided, and we had tested it on different excitonic models before, so I decided to continue using it. And the advantages I had mentioned is that I didn't mention the number of oscillators we had in the bath, but in each bath we had, let's say, up to 100 oscillators. And we can, let's say, down the road, consider more realistic baths or, with different spectral densities. So we can actually treat those degrees of freedom more explicitly than just by putting in some, I don't know, dissipative term into a Lindblad master equation or something like that. So that's one of the advantages that we gain using a mixed quantum classical method. That being said, we're also using Lindblad master equations now to study charging, which
So let's thank our speaker once more.